Hello students of statics, welcome to this lecture today, this video. We're going to talk about equivalent transformations. The cool thing about equivalent transformations is that you already know how to do these. You've actually been doing them on multiple topics for quite a while, but we're just highlighting that there's a group of things you've been doing on a variety of topics that we can all call equivalent transformations. So let's define equivalent transformations. This is when different loadings now keep in mind when I say loadings, we mean combinations of forces and or moments. Okay, so we lump all things together. Forces and moments are loadings. Have the same external effect on a body. So one term I'd like to highlight in here is this word external. So it turns out for the vast majority of statics, we are going to focus on external effects, external forces, external moments, external couples, external resultant forces, all these things on the outside of a body. And fundamentally, we need to understand what's going on the outside of a body before we can understand what's going on the inside. So to contrast internal and external, and this would be the same example that we use in our textbook, is that if you get your car stuck in the mud, okay, and let's say that there's two different engineers in the car, and one of them says, let's pull it out by the bumper, and the other one says, let's push on it by the back. Okay, so one wants to pull in the front, one wants to push in the back. Now the external effect of both of these actions, okay, so let's go ahead and draw this. We'll go with kind of a simple Jeep looking, kind of low clearance there if you're stuck in the mud. So if someone is pulling on the front with a force, F1, and pushing on the back with F2, and there's some kind of resistance force, we'll just put an R down here. So that's not for resultant, but that's just for resistance of why we're pushing or pulling on this car. That F1 and F2 will have exactly the same external effect on this body. Okay, pick either one, they'll have the same external effect. But their internal effect could be very different, right? If you're pulling over here on F1, you might pull off the front bumper. If you're pushing back here on F2, you might collapse the rear bumper or the rear of your vehicle, right? So they're going to have a different internal effect. And also how the tension and compression manifest themselves through the frame of this car are going to be very different between pulling and pushing. Okay, so that's the difference between external. These are externally equivalent, but internally they're different. And it turns out we have an entire chapter devoted to the internal effects of forces. We'll look at internal tension, internal compression, internal bending moment, and internal shear. And so that'll be coming up a little bit later in statics. But for now, we can just say that we're focusing on these external effects on a body. And so some of the transformations that you've already been doing are the following. One transformation that we learned early on is vector addition. If you take two forces that are concurrent with each other, basically going through the same point, that you can add those together, end up with the resultant force, and the resultant force and the two original forces are equivalent, right? Another thing that we could do going in the opposite direction is we can break a force into components. So that's to say, if you have a force here, call this force F, and I break that into F sub Y and F sub X, given you've created basically a parallelogram that's exactly the same size as your original one, those two systems are equivalent. A third transformation that we've done this one since early on as well, is to slide a force along its line of action. And we've shown this a good number of times. Basically, just by moving a force along its line of action, as long as you don't change its sense, as long as you don't change its line of action, and you don't change its magnitude, it's still an equivalent force. Another way that we've done transformations is by swapping a force couple with a couple moment. So this is just saying if we have two equal, opposite, and non-collinear forces, so magnitude of F, that I could swap those out. Go ahead and practice the right-hand rule on this. This gives me a positive or negative right-hand rule from this pair of forces. Should end up with your thumb into the screen, and so we could show an equivalent couple going in the negative right-hand rule direction. I could label that as couple. And of course, that's going to be equal to the perpendicular distance between those two times the magnitude of one of the forces. But once again, these are equivalent, just like these up here are equivalent. Another transformation that we've done is to find a resultant moment. Just like finding a resultant force is just adding together the forces, finding a resultant moment is doing the same thing. Don't forget in your resultant moments to add together both your R cross F moments and also your couples. And then number 6, we can also break a moment into components. And this would show, I'll draw a little sketch here, that if we have an axis system, so X, Y, coming out of the page here is Z, and let's say we have a moment using the double-headed arrow notation going off this direction, adding a ghost box here. Let's say here's the front face of our box, coming back to the y-axis, something like this, putting in the back corner here. So this moment would have a negative component about the x-axis, positive about the z, and positive about the y. And essentially we could create an equivalent system using the same 3 axes and show that's equivalent to having, so here would be our m sub y. We said that the m sub x is negative, so here is our m sub x, a positive z, m sub z. So as long as we obviously scaled these values of the components to the overall moment vector, we could create this equivalent system. Okay, so all these being vectors. So really the same kind of idea we did for a force, breaking the components. We can break a moment into components. You can do that in 2 dimensions or 3. It really makes more sense to do it in 3 because in 2-dimensional space, as long as all the forces are in the plane of the page, then all the moments are perpendicular to the page, and so there really isn't a second component. There's only going to be a z. So that's why we focused here on the 3-dimensional moments. So that's the basic idea of transformations. We've been doing them. I'm just highlighting that they're tools that we can use to transform different force systems. And one of the reasons that we want to transform force systems is we want to come up with statically equivalent systems. Now, there's kind of 2 directions we can go. We can either test if systems are statically equivalent, or we can also try to create statically equivalent systems. The basic process to compare for equivalent loads Now you might even know the answer to this. What do you think is the basic process? What things would you compare if you wanted to find out if you had equivalent loads? Turns out that one of these things to compare is that the sum of all forces, and I'll put a sub 1 and a sub 2. So all the sum of forces in system 1 is equal to the sum of all forces in system 2. Now, if you had a two-dimensional system, you want to compare both the x and y. In a three-dimensional system, you want to compare the x, y, and z. So in words here, we could say that the resultant forces are equal. And you're probably, if you didn't get that already, you're like, oh, if the resultant forces must be equal, also the resultant moments must be equal. Now we do need to select the same point. Okay, so I'm going to put a moment about point P for body 1, or system 1 is equal to the moment about point P for system 2. I do need to squeeze in here a summation sign, a large sigma. So that's basically saying that the resultant moments equal about the same point. And we know that moments vary by value depending on where you take the moment about. And that is true specifically for R cross F moments. For couples, it doesn't matter, right? Remember that a value of a couple subjected to a body is exactly the same, no matter where you sum moments. Now, different textbooks use a variety of language to talk about finding statically equivalent systems or fundamentally finding resultant forces. So the following three statements say the same thing. So here we have some equivalent phrases for equivalent systems. One of those is to find the equivalent resultant force and couple moment through point A. A next one would be to say, replace the loading or the individual forces and couples with an equivalent force couple system at point A. And then a third way of saying the same thing, and honestly I prefer the third one, it's the simplest, is to find the resultant force and moment about point A. Okay, but all of them are fundamentally saying add together the forces, add together the moments, and make sure that you add the moments around point A. Okay, so any of these three things, realizing that the reason they're using the first one here, this couple moment, is that once you find a resultant moment, you're basically saying that, hey, that's a pure moment around a given point. Now, not all force systems can be resolved into just a moment, It turns out that need to resolve into a moment plus a resultant force. Now, you may also see in some textbooks discussions about moving resultant forces to cancel resultant moments. To be honest, in my classes, I don't get into that topic because I think it's a dangerous idea of being able to get rid of moments. I know that all static students would love to get rid of moments, so it gives you the idea you can get rid of moments in all cases, but it's a slippery slope. It's a dangerous idea. And so the language I'll try to use most consistently will be to find the resultant force and moment about a point. But once again, all three of these things are saying the same thing. So let's go ahead and combine these two topics, this idea of equivalent loading and this idea of statically equivalent systems on the following example. All right, so we have two different bodies. Now these bodies have the exact same dimension. Doesn't technically matter if you're talking about equivalent systems if the bodies have the same dimension, but it makes it a little bit easier as long as fundamentally the resultant force and resultant moment about a given point are exactly the same. We can say that the systems are equivalent. And so I'm telling you that these two systems are equivalent, but we have a few things that are unknown. We know all the loading happening at one. We have two horizontal forces, one 10 kilonewtons horizontal, another 5 kilonewtons going downwards. On system 2 or body 2, we only have one known force, 10 kilonewtons pushing over to the right. And then we have two unknowns. We don't know the direction and magnitude of F, and we don't know the direction and magnitude of C. So on these problems, what we really want to start with is coming to one of the bodies, in this case the one that we know is complete, and we want to find the sum of forces in the X. And of course in this one it's fairly straightforward, sum of the forces in the X. Now we're assuming a horizontal vertical axis system. Anytime that you go to write this sum forces in the X, double check that you have an axis system. That's the tool that I actually use to always confirm when I need an axis system and when I don't, is when I go to use it, right? Because fundamentally I'm using it by writing this equation. And so summing forces in the X, we have a positive 10 kilonewtons, and there's only one force. And then I'm going to sum forces in the Y. Of course, summing force in the Y, again, here is a fairly simple system, but I only have one force, so I have a negative 5 kilonewtons in the Y, and then I sum my moments. Now, as long as I pick the same point on both bodies, I can sum moments by any point that I want. I went ahead and located point A for this problem. So if we take a look at these two moments, it turns out, actually, see if you can answer this before I tell you the answer. What is the moment of the combined moment of both these forces around point A? Go ahead and see if you can answer that. Pause the video if you need to. So coming back from that pause, it turns out that the line of action of both of these forces goes through point A. And so our sum of moments about point A is equal to 0 kilonewton meters, because neither one of these forces cause a moment around point A. Now, other points in this body will have a resultant moment. This point does not. And so as we go over to the next body, and we want to sum our forces in the X and see what we get, it turns out that this also has a positive 10 kilonewtons. So that one checks off. That one is equivalent. Summing forces in the Y, we have an unknown value of F. Now we've drawn it upwards. Let's keep it going that direction. We'll call it positive. And we know this needs to be equal to our other resultant, right? This negative 5 kilonewtons. So this is equal to negative 5 kilonewtons. So another way I could write this is that F is equal to negative 5. Now, what the negative 5 tells me is that the magnitude is 5, and it's going in the opposite direction than I drew it. So this would be F is equal to 5K. And I think obviously you could see that that's going to match up with the one in the other body. And then the last step here is to sum our moments. And so summing moments about point A. Now this one will create some moments. I have a 3 meter distance. I'm going to use the known value here of F going downward. So that will give me 3 times 5. And from the right-hand rule, that sign is positive. Your thumb should come out of the screen. And then the 2 Newton meters times 10. So 2 times 10. And that one's going to be from the right-hand rule, 2 crossed into 10 is also positive. So basically I have 15 plus 20 plus, and I'm going to assume on this one it's unknown, so let's just list it as C. Okay, and this is once again going to equal 0, just like this one over here equaled 0, equal to the same amount. So this is not yet equilibrium, but this is equivalency between systems. So now we just need to solve for C, and we find out that C is equal to negative 35 kilonewton meters. Okay, so it turns out that negative couple would be going in this direction right here, and the value there would be 35 kilonewton meters. Okay, so that would be the correct directions. Our force vector would be going downward, and our couple at point C is 35 kilonewton meters, negative from the right-hand rule. And of course, we can move this couple anywhere we wanted. I could simulate that here. And essentially just saying that I could move it up around point A, over at F. It wouldn't really matter where I put it. It's still going to have the same external effect on our body. So hopefully that brings together these ideas of equivalency and also being able to find resultants and kind of bringing those into the concept of statically equivalent systems. And so you can see we're starting to bring the pieces together, not just forces alone and not just moments alone, but bring them together. Because the next topic we're going to get into is we're going to get into equilibrium. And so in equilibrium, we're going to create free body diagrams of these rigid body systems. And then the resultants are going to equal 0, right? The sum of all forces and sum of all moments equals 0. And that'll be coming up in the next video. Thanks for your attention today.